Hello, this supplemental video for our lesson on exponential modeling. We'll get into an alternate response to a textbook exercise that you probably did for homework recently. A very quick word on why we need b to be greater than 0 when we're dealing with exponential functions. And finally, a few more examples on exponential growth / decay models. But first, I want to show you a quick video clip of sand pendulum, or if you want to use a more mathematical term, Lissajous curves. I'm sure I'm butchering the pronunciation of that French name. Do a web search on either of those and you'll find some interesting stuff. But I bring it up at this time because this video that I'm showing now, and I'm assuming the original poster will be okay with me hijacking the content for educational purposes. I'll put the original link in the video notes. But I think this is a wonderful example that links our previous topic that we studied to the current one. When you look at this pendulum, whether you look at the left-right motion or the forward-back motion, this is harmonic motion. This is motion that would be modeled by sinusoids. However, I would not call it simple harmonic motion. Remember, simple harmonic motion means that the amplitude is constant. Yet as we watch this pendulum, we see that the amplitude, again, whether you're talking left, right, or forward, back, the amplitude is definitely diminishing over time. So that's where exponential decay comes in. And if you wanted to model the motion of this sand pendulum accurately, you'd really need a combination of trigonometric or sinusoidal models multiplied by an exponential model. And really, if you wanted to get the left, right, and forward, back motion all at once, you would use parametric equations, which we will get into at some point if you continue on to BC calculus. Anyway, let me get on to an alternate response to textbook exercise. All right, in recent homework, I had a student several years ago who gave an interesting response to this question. So what I was expecting and what the textbook authors were expecting when you were asked to state which transformation we see when we go from this original curve to this transformed curve, we're expected to say a horizontal translation of 3 units to the right. We've done plenty of that this year, and that's what I think would be obvious to most students. But I had a student some years ago, I won't reveal her name here, but I had a student who said that it represents some sort of vertical shrink. And it turned out she was correct. Now, I'm not sure why she chose to go that route, which was the less obvious route, but here's the case for that. It really comes down to our properties of exponents. Quick reminder with this table from the prerequisites chapter in our textbook. Those properties of exponents may be used to show why we can look at this function as either a horizontal translation or a vertical shrink. According to the quotient property of exponents, we can think of that 2 to the x minus 3 power as 2 to the x divided by 2 to the third. And of course, that 2 to the third on the bottom can be thought of as 8. And we can rewrite that whole thing as 1/8 times 2 to the x. So this student from several years back claimed that the function g of x represents a 1/8 vertical shrink of f of x, and she was correct. As were all the students who said the more obvious answer of 3 units translated to the right. Now, this either-or condition, this specific either-or condition, really only applies to exponential functions. Let's take a look at this visually. I'm going to take one copy of this curve and move it 3 units to the right. And I'm going to take another copy, this red copy, and I'm going to vertically shrink it. So notice that as I have it drawn, it's about 8 units tall on my graph. But if I grab it here in the software and vertically shrink it gradually down so that it's 1 unit tall, we see that it lies right on top of the other copy. The blue copy and the red copy both are coincident with each other, indicating to us what we already determined algebraically, that you may look at it either way. Okay, moving on. I'll be very quick here. Just wanted to really highlight this definition of exponential functions, which we've been using, where we said that an exponential function is any function that may be written in the form of a times b to the x. And something that I kind of glossed over earlier, but I want to call attention to now, is that notice that the definition requires that b is positive. And rather than me elaborate on it for too long, I'll invite you to play around with it a little bit. Let me show you a quick image of what happens when you let b be negative. So here's a picture, a calculated picture of y equals quantity negative 2 to the x power. Notice that if those parentheses weren't there, that would be a different function. But when you have the b value, in this case, a would be 1 and b would be the negative 2 there. When you have the b value negative, you get some interesting results like you see on the screen now. If you're trying to replicate this on your calculator, notice that I have this set to zoom decimal. If you had a different window settings, you probably wouldn't see any points at all. And I would also invite you to try to figure out what's going on and why we see this result. You may try to trace to certain values. For example, I would invite you to trace to x equals 4/5. Also trace to x equals 3/5. And also trace to x equals 3/4. And you should see three different kind of results from those three different numbers. And I would encourage you to think of why did those three different simple fractions yield three different results. But at the end of the day, I think what you'll find is a reason as to why we're going to stick with just positive b values, because you get into some crazy stuff when you let b be negative. All right, moving on to our examples for today. In this chapter on exponential and logistic modeling, for this video, we're just going to stick with the exponential modeling. Let's start with bacteria. And by the way, this is something that you've seen in Algebra 2 before, so if it seems familiar and you think you got a hold of this on your own, then good, but this is a refresher since it's been a little while. Let's say we're dealing with, let me get this picture out of the way, I know nothing about any of that stuff, I'm just a math guy. Let's say we have 100 bacteria in a petri dish and the culture doubles every hour. Predict when the number of bacteria will be 350,000. Now, if you're comfortable jumping right into the equation and that equation makes complete sense to you, then go ahead and do that. But for the student that's just a little stuck right off the bat and not sure where to start, I would say always feel free to start with a table. Kind of get your feet wet with some actual numbers. This may not be the most efficient way to go, but it's one that I think deepens your understanding. So let's make a table for time, and then I'll use P for population of bacteria. So I'll say P of T represents the number of bacteria. And I know that when T equals 0, and I should be clear, this is time in hours, we're starting the stopwatch right when there are 100 bacteria, so I'll put 100 in this column. And if the bacteria double every hour, then I know after 1 hour has passed, I'll be up to 200 bacteria. And after another hour has passed, I won't be up to 300, that would be a linear function. But when this doubles again, demonstrating exponential behavior, we're up to 400 bacteria, and so on. After 3 hours, 800. After 4 hours, 1600, and so on. So if you watched all the previous videos, or if we've gone over this live in class, you'll recall that the output value corresponding to an input of 0, the output value there, that's our initial value, was the vocabulary word we used. And when you're writing y equals a times b to the x, a was the initial value. In this case, I want to use the notation p of t equals, I'll say a times b to the t power. And again, the a we now have is 100. With this table in front of us, I'll remind you that whatever you're multiplying by, whenever the input column just increments by 1, whatever you're multiplying by in the output column, that is your b value. And we are multiplying by 2 every time here. So that means b is equal to 2. And our equation is p of t equals 100 times 2 to the t power. If I want to know when this population will reach 350,000, I could do this algebraically, and in a later section we will. We could set that equal to 350,000. And that's where, if we're pursuing this algebraically, logarithms would eventually come into the picture. And if you want to go ahead and start practicing that, of course, I won't stop you from doing that. But for right now, let's go ahead and make sure that we're good doing this graphically on a calculator. Here's the function 100 times 2 to the x typed into the calculator, as well as the target value of 350,000. If I look at the table and scroll down to see where does it look like those values in column 1, y1, reach and surpass the 350,000 in column 2, looks like somewhere around there, when the input is 12, it looks like the y1 column surpasses the y2 column. So I need to make sure that my x max is greater than 12 and that my y max is greater than 350,000. So there I've set my window settings, and let's see what the graph looks like. There we have it. And from here we'll go to Calc Intersect. And there's our intersection at x equals 11.773. Or within the context of our problem, we'll say t equals 11.773 hours. So I repeat, at some point we'll start coming up with that same result by using, we'll do it algebraically using logarithms, but for right now, feel free to go ahead and just use your calculator. Now here's a modification of that same example, and if I once again make a table of values, 4,800 is my initial value when t equals 0. And I guess before I plow forward, I should highlight what's different in this modification. That first of all, we're starting with 4,800 bacteria, and instead of doubling every hour, I have it now growing by 25% every hour. So let's give a little thought as to what number should appear in this, what number should appear next in this output column. Well, after 1 hour, we're going to still have the original 4,800. But on top of that, we want to add 25% of that 4,800. So I'll say plus 4,800 times 25%. I'm going to write here for emphasis that I'll take 100% of that original 4,800 and then add on top of that another 25% of that same 4,800. So adding them together, I would think of that as 4,800. I'm going to consider that my greatest common factor and pull it outside of some parentheses. And on the inside, I have 100% plus 25%, or I can go ahead and just combine those into 125%. Rather than compute the actual value of that simplified any further, I'm just going to keep it in that form, 4,800 times 125%. And actually, let me go ahead and take the opportunity to rewrite that. Instead of 125%, I'll go ahead and convert that into decimal form, 1.25. And then I'll argue that in the next column, I'll take that value, 4,800 times 1.25. And in order to increase that value by 125%, I would need to, using similar reasoning, I would need to multiply that by another 1.25. But of course, we know it's more efficient just to write 1.25 squared. And you see where this is going. The next column would be 4,800 times 1.25 cubed, and so on. So in general, for any time t, the bacteria population would be 4,800 times 1.25 to the power of whatever t is. That is going to be my bacteria population. Once again, I'll go back to the calculator. I'll type in that the equations, 4,800 times 1.25 to the x, as well as the target value this time of 80,000. I go to the table and look for where does it look like the values in this column are going to surpass the 80,000 in the column to the right of it. Keep going, keep going. The numbers are getting bigger and bigger, and it looks like somewhere between 12 and 13 this time. Somewhere between 12 and 13, those values are surpassing 80,000. So the Xmin and Xmax I had left over from last time are good. This time I'll just make this 90,000, a little bit higher than the 80,000 target. And we'll once again use calc intersect to find that the intersection occurs this time at 12.608. So our answer here this time is t equals 12.608 hours. And as the disclaimer I always give is that this 3 decimal place approximation is due to the rounding policy of the AP calculus exam. In real-world scientific context, there are some really strong arguments to be made that I'm using way too many significant figures or decimal places, but I'll stick with the AP standard for now in math class. Our textbook, if you're willing to peruse it a little bit, uses a similar building up approach to ultimately reveal a formula for population growth. And rather than just mindlessly plug numbers in, I hope you'll connect it to the example we just did and really think about why each piece of this formula makes sense. In the previous example, the 4,800 was the P0, the initial population that appears in this formula. The 100%, the fact that we wanted to keep the original amount and add on top of that an increase. That's why the 1 appears in this formula, since 100% equals 1. And then that 25% rate of increase is represented by r in this formula, all raised to the power of t. So with that in mind, rather than me talk on endlessly about it, I'm just going to flash some examples already worked out quickly on the screen here and ask that you study them a bit and make sure that it all makes sense. In this first example, where they're giving population models for San Jose, California, the biggest city in Silicon Valley where I grew up, as contrasted and compared with Detroit, Michigan, we see those two population models. What should stand out to us is that the 782,248 is the initial value, the initial population of San Jose. I don't know when they're starting, what they consider the starting year to be. But we see a growth rate there, that's 100% plus some percentage amount. And then Detroit started with a higher population, but then we have 100% minus some percentage there. But let me refrain from getting into any more detail. Pause this, take a look at it if you like, and let me go ahead and reveal my work for it now. Again, initial value, population growth here for San Jose, initial value and population decay rate for Detroit. A reasonable question to ask would be, hey, if San Jose was growing and Detroit was decaying, but Detroit started with a higher population, at what point would San Jose overtake Detroit in population? And you can try it out on your own on the calculator, type in those two equations, do calc intersect. You should find, about to reveal the answer here, that after 15.542 years from the beginning, from t equals 0, is when those two cities would intersect in population. But one certainly has to keep in mind that these are just models and they don't have perfect power to predict the future. And in fact, if we look at the actual populations of Detroit and San Jose over the years, we see that San Jose experienced a slight bump in the early 2000s. That was the dot-com boom, the internet bubble. But Detroit suffered some serious population decay between 2000 and 2010 or so. And of course, we're familiar with that in New Orleans as well, with Katrina and all back in 2005. So these are just models, but don't mistake them for perfect predictors of the future. Okay, I'm going to end with this one more example that I'll just flash on the screen there. I'll let you pause it, take a moment to read it, and then I'll display my solution. Of course, if you have any questions on any of this, please do attend the office hours or reach out for help. All right, here is the solution to this problem. All right, bye for now.